All right, friends, welcome back. So, we've been talking about identifying the HOMO and LUMO of organic molecules and thereby predicting reactivity. And this is a new concept, so it's okay if you're a little bit unfamiliar with it, if you're worried about it. Let me take it back and even to a simpler level. And let's ask the question, what would happen if I took, and I think we actually did this last time, what would happen if I took a helium atom and a hydrogen atom and I tried to bring them together to make a bond? So as you know, helium comes with two valence electrons. This is, our dotted line here is sort of our break-even point. I'm showing you where the non-bonded atomic orbitals would be. And then over here on the right, we've got hydrogen ion, or you can call it a proton. The helium comes with a 1s atomic orbital that's filled. The hydrogen also comes with a 1s atomic orbital that's filled. When we mix them together, we get the plus combination that's lower in energy and the minus combination that's higher in energy. But because I only have two electrons, mixing these together actually allows those electrons to go lower in energy, and the minus combination is unfilled. This would be our sigma bonding orbital. This would be a sigma star. And what we've just predicted is the existence of what we might call protonated helium, which exists, but mostly in space and not for very long. Okay? But the principle here is that when you have a bonding, or when you have a filled orbital interact with an empty orbital, the plus combination goes lower in energy, the minus combination goes higher in energy, and the electrons move down to the lower energy plus combination where they're more stable. Yeah, go ahead.
So this is just more a question of curiosity, because I mean we just proved like it's more energetically favorable to have that bond, but you said it lasts for a couple seconds really, and it's like why?
Well, okay.
It's favorable in that case.
Okay, why does it last? So the real question is, how favorable is it? I don't actually know the bond energy. I don't know how low it goes versus, and the idea would probably be you've got a couple of things to deal with. Yes, the electrons can move lower in energy, but the molecule you make has a positive charge on it, and so there's some offsetting things. In terms of how long it lasts, actually, kinetics or how fast something happens are actually not always related to how stable things are. So what I'm going to recommend is Googling it and seeing what you can find out. There's possibly a Wikipedia article on that subject. But what I want this to demonstrate is it's sort of a way of restating the first and great commandment of organic chemistry. When you have overlap, or another way of saying that is interaction between a filled orbital and an empty orbital, you're going to get a filled bonding orbital and an empty antibonding orbital. And that's a stable situation. That's a favorable situation. In contrast, what would happen if we change this diagram so that over on the right we had helium and we tried to bring two heliums together? Two heliums, helia, I don't know. What have I got to do now? Right? Yeah, I have to take when I mix two orbitals together, the plus combination's lower in energy, the minus combination's higher in energy, but I have 4 electrons instead of 2. So I populate both the lower energy one and the higher energy one. The higher energy one is always further above our break-even point than the lower energy one is below it. And so populating that higher energy one just completely abolishes the bond. And that molecule is not stable. It flies apart. And so, hold on. What we've just demonstrated there is a concept called closed shell repulsion, that if you have overlap or interaction between two filled orbitals, it's very destabilizing. That's often called closed shell repulsion. The idea that if something has a full octet or a full set of valence electrons, it's not that interested in bonding with other stuff. Go ahead.
What if it's a helium plus?
What if you stole an electron? Ooh, all right, yeah.
What if it's a helium that's with a filled orbital and the helium with just one electron?
Yep. Then you would have, technically, I suppose you would have basically half a bond. So it would be stabilized by half of a bond instead of a full bond. Does that thing exist? What if it was helium 2 plus? Okay, fine. Yeah, sure. Yeah, go ahead.
So if there's 4 electrons, why doesn't like 2 go into the bonding and then they go into like, the one has, they don't exist anymore?
Exactly. Good. So the question was, well, why can't I just put 2 here and then put another one up here? No, these become the plus and minus combination. Yep. All right. What else? Okay. So let's do some more examples. Let's see. Sure. Let's take this molecule. You don't need to know its name, but it's called methanol. We will abbreviate it as MEOH or CH3OH. Got lone pairs on the oxygen. Just thinking through, I've got some sigma bonds here. I've got an oxygen-hydrogen sigma bond. I've got an oxygen-carbon sigma bond, and I have 3 carbon-hydrogen sigma bonds. Now, they're not probably equal in energy. There's some difference between them. The 3 carbon-hydrogen bonds are probably equal in energy. Oxygen-carbon bonds are actually a little bit lower in energy than carbon-hydrogen bonds are, and same with oxygen-hydrogen bonds. We're not going to worry about that distinction because it's not going to matter. Each of those sigma bonding orbitals is filled, and we have corresponding anti-bonding orbitals, which I won't label, I'll just call them all sigma star. But the one thing I haven't accounted for is these 2 lone pairs on oxygen, and those show up where? At my 0 position, my break-even point, right? So I've got 2 lone pairs. So what is the highest occupied molecular orbital for methanol? It's the lone pair electrons, right? That's the highest occupied molecular orbital. Okay. Which is the lowest unoccupied? Well, it would be one of the sigma stars, and it's not immediately clear to you what that would be, and we're not going to worry about that for right now. All right, let's do this fun molecule. Fun. Fun is always relative. Okay, this is BF3, boron trifluoride. Notice that boron usually comes with 3 valence electrons. In this Lewis structure, it owns only 3, so boron has a neutral 0 formal charge. That means boron is surrounded by 3 groups and must therefore have what geometry? Has to be trigonal planar. Therefore, what is the hybridization of boron? Sp2, which means I've got 3 sp2 orbitals and 1 2pz orbital, we'll say. We'll say that all of these are sp2 orbitals in the xy plane. So if we envision boron as being trigonal planar and this is the xy plane, then each of those bonds between boron and fluorine come from an sp2 orbital on boron and then an orbital on fluorine. So what I'm saying is each of the 3 sp2 orbitals are going to become a boron-fluorine bonding orbital. And then I'm also going to have 3 antibonding orbitals, right? So for each sigma bonding orbital, here is our break-even 0 point. Here are my 3 boron-fluorine bonding orbitals. Here are the corresponding antibonding orbitals. And those bonds are full of electrons. All right, what else am I missing? What about that 2pz orbital? Is it still there?
Yeah.
Sure. Does it have electrons in it? No. Oh. So you mean you can have an empty atomic orbital sitting on an atom? Exactly. This 2pz orbital is still there, but we don't have any electrons for it. So we're going to put that here. I guess I need my dotted line to be gray. So here is an empty 2pz orbital. I also made the unfortunate choice of putting fluorine there. I should have chosen hydrogen because then we wouldn't have to deal with this. But there are lone pairs on the fluorine. There are 9 of them. And so those are also going to show up about here. I'm just going to call these the 9 fluorine, except I can't spell fluorine. Lone pairs. Does that sound ominous to anyone else when I said the 9? Yes, okay. No. My office is filled mostly with Star Wars memorabilia. However, my son several years back made me a homemade staff of Saruman, so that's also there if you want to come see it. It's made of cardboard. You can't stab anybody with it, which is somewhat disappointing, but what are you going to do? Okay, I'm kidding. I don't stab people. Go ahead.
So shouldn't boron have like an extra pair of electrons to fill its 8? Because right now it doesn't only have 6.
Right, so the question is, would boron want an extra pair of electrons to fill its valence? Well, if it did own 2 other electrons, it would have a 2- negative charge. So offsetting factors, right? But you're right, it does have an empty 2pz orbital. And we would call that the LUMO. And notice that that empty orbital, that empty p orbital, is lower in energy than any of the antibonding orbitals. So if BF3 were to act as a Lewis acid, where is the place where the electrons would go? In the LUMO, in that 2p orbital, right? Okay. So we just made a pair of predictions. The LUMO of BF3 is this 2p orbital. The HOMO of methanol is lone pairs on oxygen. So if we use methanol as our Lewis base or nucleophile, and our BF3 as Lewis acid or electrophile, what can we show happening? Well, here's methanol, CH3OH, lone pairs on oxygen is the highest occupied orbital. Here's BF3, and its LUMO, lowest unoccupied orbital, is that empty p orbital. I'm going to redraw methanol for just a second. So here's one of the lone pairs. How we draw it isn't necessarily that important. The reaction we should predict is, and again, yay for pretend animation, electrons, whoa, and on that oxygen can dump electron density into the empty p orbital. In so doing, what is the interaction we're going to have? We're going to have the lone pair on oxygen that had 2 electrons in it with the empty p orbital on boron. As we've done before, you mix these two together, you're going to get the plus combination, lone pair plus 2p, and then you're going to get the minus combination, lone pair minus 2p. By lone pair, we mean bonding orbital. I suppose we could call it, I don't want to confuse people because that lone pair thing, you're going to think, well, is there lone pairs in both places? Non-bonding atomic orbital on oxygen, and in red is the lone pair. All right. Non-bonding atomic orbital plus non-bonding atomic orbital minus, only now it's not non-bonding anymore, so we're really confused. What should we do? Should we just pretend that these lone pairs are in an sp3 orbital? That's probably better. So you've got the sp3 plus the 2p. The plus combination is the bonding one. The minus combination is the anti-bonding one. Because we only have 2 electrons here, we form a new bond. And so actually, what is the new structure? What is the product? Well, you can predict it now based on what I just told you. We made a new bond between boron and fluorine. I'm sorry, boron and oxygen. Boron used to be surrounded by 3 things. Now it's surrounded by 4, so that means it has to be now sp3 hybridized and tetrahedral. And if we assign formal charge, we would see that boron has a negative formal charge and oxygen has a positive formal charge. If that's confusing to you, go back and review formal charge and practice till you got it, okay? So this is another example of nucleophile attacks electrophile and we get a bond. Okay? All right, what else? Yeah.
In the example right before, you said that, that one right there. You said that the oxygen and carbon sigma bond would actually be lower in energy.
Yeah.
From what I was reading, I would think that they'd be a little bit higher in energy.
Okay. All right, so this is a minor point that again, I'm not going to push you on that distinction, is which of these sigma bonding orbitals is lower in energy. You can go look it up in a table and it will tell you.
Okay.
But here's a general principle. And this is an aside, so don't worry if it doesn't make sense. If I compare making a sigma bond between an sp3 orbital on carbon and an sp3 orbital on another carbon, here's my new sigma bond. But what if I, instead of doing that, what if I want to make an orbital, starting with the same sp3 carbon, but what about the atomic orbital on oxygen? And here's where there's a sort of way to think about this. Electronegativity literally means that electrons on that atom are lower in energy and closer to the nucleus. Therefore, the starting position of the oxygen orbital is below the carbon. And what that means is when we go down and make the plus combination between sp3 of carbon and sp3 of oxygen, that actually ends up lower in energy than the sp3 of carbon plus the sp3 of carbon.
Okay, because in the review, in the molecular orbital theory study guide, it says that carbon bond with an X group sigma bonds are higher in energy than carbon hydrogen or carbon carbon, where
Okay.
the X bond is like an OH or something like that.
Yes, and you can continue to think of it that way. The only thing is I learned something from a grad level class that I taught in the past couple of years, and so I should have revised that portion, but it's fine.
Okay.
The reason, and don't worry because I'm going to give you an example of that. The reason we worry, the reason that becomes significant is just when the minus combination of carbon plus carbon is up here. The minus combination of carbon plus oxygen is there.
Yeah.
In other words, the electronegativity of oxygen relative to carbon takes the plus combination and the minus combination and moves them both lower.
Okay, so it's going to impact the LUMO.
So it's going to impact the LUMO, yeah.
But we don't have to worry about it as far as
Don't worry about the bonding
the
orbital.
bonding, just the antibody. That's
Yeah.
okay.
Yeah. So I'm sorry, that was a bit of an aside on something that we haven't totally talked about yet, so don't worry about it. We'll come back to it. Or maybe at all. Okay. Sorry about that. What else? Yeah.
Going back to when we were doing these two molecules individually, sort of, how did you know that the oxygen was not hybridized, or it was hybridized?
Okay. Well, so what do we know about that oxygen? It's surrounded by 4 groups.
Okay.
So 2 atoms and 2 lone pairs. So you can think of it as being tetrahedral and sp3 hybridized. Technically, when you talk about geometry, it's only about the atoms because you can't see lone pairs. So you've probably heard of an oxygen bonded to 2 things as being bent.
Yeah.
Yeah.
Okay, so if there was a lone pair on the bromine, that would also...
On the boron?
Boron, sorry, yeah.
Yeah.
The boron, then all of that would be hybridized, but because there's nothing there, it's not hybridized.
Right, yeah. So the question is, why is that extra orbital on boron a 2p orbital? And that's because we don't have electrons to put in it, so there's no repulsion, and the best arrangement is trigonal planar.
Okay. So, and just to cover all my bases, if we took one of the lone pairs off of the oxygen in the other molecule, then there would be an empty 2pz.
That's right, but you'd have to have oxygen 2 plus probably if you did that, and that would be
Okay.
sad.
And then I'll come back.
Okay.
Thanks.
Okay, yep. Others? Yes?
You know, when you combine the 2 molecules, can you explain why the oxygen is positive and not 2 positive?
Okay, why is the oxygen positive rather than 2 positive? When we assign formal charge, an atom owns all of its lone pairs and half of the electrons in its bonds. And when we calculate formal charge, we're going to compare how many it owns to how many it usually has. So oxygen usually has 6 valence electrons, but it only owns 2, 3, 4, 5. So that's where we get the +1 charge. Similarly for boron, boron usually has 3 valence electrons. Here it owns 4. 1, 2, 3, 4, and that's where we get the -1 charge. Yeah?
Just out of curiosity, you talked about how making bonds stabilizes things and makes a bonding orbital strength slower, but in this case, would it still not be favorable to the ceramic magnet because now you're creating those hydrogen on different molecules? Like, would that be an unfavorable reaction?
Okay. Yeah, the question is how stable really is this bond, because we went from something that was both neutral to now something that is charged. That's a good question, and the answer is known, but you'd have to look it up. Because in our simplified picture of making these bonds, yeah, it's the electrons that used to be up here that are moving lower in energy. But there are also other things going on in the molecule that we may not have accounted for. For example, we're changing the geometry. The boron, instead of being trigonal planar, is now tetrahedral. If you think about that, that's going to bring these electrons closer to each other, so there's some repulsion there. There's a lot of different things that can happen. We're going to get better as we go along at estimating how stable various intermediates are, but that's going to require us to delve into pKa's and some acid-base chemistry, which I optimistically thought we would do today, but is clearly not going to happen. Okay, saw another hand. No? Nothing? Okay. All right. So we've seen a couple simple examples of reactions where HOMO attacks LUMO. I want to show you a couple of different ones, but before we do that, I want to summarize what we've learned about orbitals in organic molecules. If here we have our break-even point, we'll call that sort of the messy middle. Then below that, we'll have our, I don't know, this is kind of a yuck color. I try to avoid red and green because of red-green color blindness, but sometimes it just can't be helped. Or rather, I choose not to worry about it. So here we're going to have the domain of the bonding orbitals. Here we're going to have the domain of the non-bonding atomic orbitals. And up here in this lovely rust color, we're going to have the domain of the anti-bonding orbitals. In terms of relative stability, and on this axis we're going to have energy. What shows up here in the middle region? An empty p orbital. An empty 2p orbital will show up there. Also, lone pair electrons. Okay, they both show up sort of at this intermediate level. We're not going to worry about whether one's higher or lower than the other, just that they both are in this mid region. We're going to see in general that sigma bonding orbitals are the lowest in energy because they're held close to the nucleus. If a molecule has pi bonds, they're going to be higher than the sigma bonds. Similarly, most of the sigma bonds, carbon-carbon or carbon-hydrogen sigma bonds, are going to have corresponding sigma star bonding orbitals that are quite high in energy. Almost never will the LUMO be a carbon-hydrogen bond. And sometimes the pi star will always be lower in energy than the sigma stars. Okay. So we can start to make some predictions based on structure without going through that whole analysis and drawing out the MO diagram for every molecule. We simply need to start with the structure of a molecule and look at it and ask, are there any lone pairs? If there's not, then I'm going to look for pi bonds to try to find the HOMO. If there's no lone pairs and no pi bonds, probably it's not terribly reactive, and probably there's not a lot we can do with it. Then, in terms of, so that's for identifying nucleophiles. I'm looking here, right? And in particular, molecules that are nucleophiles are going to have high energy lone pairs or maybe pi bonds. That's like true for most of the reactions you'll learn in this class, both this semester and next semester. What about empty orbitals? Well, first I'm going to look for an empty p orbital. Those are rare. It's either on a neutral boron. An example of that would be, as we've shown you before, on a neutral boron. Another place that there's an empty lone pair is on a carbocation. We haven't learned anything about carbocations yet, but they also have an empty p orbital. And if you go through and understand what that formal charge means, you'd realize that carbon's only surrounded by 3 groups. It's got to be trigonal planar, got to have a p orbital, and that p orbital is empty. If there's no empty p orbital, I start looking for pi stars. If there's no pi star, no empty p orbital, there's one more thing I look for. And to see how this happens, remember what I told you, that if we were to rank orbital energies, let's just imagine for fun sp3 hybridized orbitals on carbon versus nitrogen versus oxygen versus fluorine. If this is sort of energy here. Electronegativity literally means electrons on that atom are lower in energy and held closer to the nucleus. There's a reason for that. It has to do with increasing effective nuclear charge. But you can think of electronegativity as just meaning how stable are electrons, non-bonded electrons on that atom. Okay? So by that analogy, sigma bonds that come from carbon bonded to something electronegative, like nitrogen, oxygen, fluorine, chlorine, are going to be lower in energy than carbon-carbon or carbon-hydrogen bonds. This is a change relative to the study guide. Fortunately, it's inconsequential. Electrons in a carbon sigma bond are never going to be the HOMO of our molecule, all right? But the electronegativity of nitrogen, oxygen, or fluorine relative to carbon will also pull down the energy of the corresponding sigma star. Right? Do you see how it's like, because of electronegativity, we took this line and that line, and we moved them down by similar amounts. That kind of idea is called perturbation molecular orbital theory. Whoops, we don't need to worry about it. Other than this is why we will sometimes see sigma stars being the LUMO. All right, so we hadn't ever so far seen sigma stars being the LUMO, with the exception of that reaction we did with water. But we're going to see pretty early on in this class, there are going to be some empty antibonding orbitals associated with CX type bonds, where X is an electronegative atom, that are going to end up being the LUMO and are going to be important. Okay? Yeah?
Is that also the case with boron?
Is that the case with boron? Well, boron's actually less electronegative than carbon. So it would actually be the other way. We won't worry too much about carbon-boron bonds. They'll show up once or twice, but not a lot. Okay? So what's my procedure now? And the study guide takes you through this. Shorthand procedure is the same for nucleophiles. I start by looking for lone pairs, then I look for pi bonds, and if there's none of those, probably it's not terribly reactive as a nucleophile. Then I look for empty orbitals. Is there an empty p orbital? Yeah, then that's the most electrophilic part of the molecule. If not an empty p orbital, is there a pi star, or alternatively, a carbon electronegative atom sigma star? What about a molecule where both of these are present? Well, that molecule would probably have two different reactive sites, and we'll deal with how to that complexity later. Okay? Yeah.
So we know if there's like a star sigma or star pi, there's just extra electrons in the electricity. Like you said, if you look for those, how do you look for those?
How do I look for them? Well, I have to remember that they exist based on what the bonds are. Yeah. So let me give you another example. Got a lot of examples in the notes, but and this is going to preview reaction types. You're going to, at some point, come back to this lecture and look at what I'm going to draw for you now, and you're going to be like, oh, we learned about that already, and hopefully that'll help. Let's think about CH3Cl. Sometimes we draw molecules in a way that represents their three-dimensional structure with dashes and wedges. Other times we are lazy. This is a lazy occasion. So looking at this molecule, if I had to say if this molecule had a highest occupied molecular orbital, what would it be? What are you going to say? Lone pair on the chlorine, right? What about the LUMO? It's the sigma star, but which one? The carbon-chlorine sigma star. The reason for that is chlorine's more electronegative than carbon, so orbitals involving chlorine are lower in energy than orbitals involving carbon. Okay, so that's going to pull the carbon-chlorine sigma star down in energy. That's going to make it our LUMO. Okay. Now let's use, this is boring, but let's use hydroxide. It's negatively charged. We could talk about the LUMO. There's only one option. It's the oxygen-hydrogen sigma star, but we don't actually care. We could tell that this molecule is going to be a Lewis base because it has a negative charge on the oxygen. The HOMO is the lone pair electrons on oxygen. So if I tell you that this molecule above is an electrophile or a Lewis acid, we're going to not care about the highest energy electrons, but we're going to focus in on the empty orbital. Very important. Okay. Similarly, if I say that hydroxide is the nucleophile, you're not really going to care what the LUMO is, but instead focus on what the HOMO is, which is lone pairs on oxygen. Okay? So now we can make a prediction. It's helpful in the early stages to actually draw what the orbitals look like. Let's draw the carbon-chlorine sigma star. The way you draw sigma stars is you put a node in between the two nuclei. And there's small lobes in the middle, and if it's not hydrogen, if the atom to which carbon's bonded is not hydrogen, then we're going to have a large lobe going back here. We can add the color as needed to get us the right changes in wave function sign. This is the carbon-chlorine sigma star. I'm also going to draw where the carbon-hydrogen bonds are. And then we can draw the non-bonding lone pair on oxygen. If you want to act like it's in an sp3 hybridized orbital, that's fine. You don't actually have to, but that'll work for us for now. Okay. Nucleophile attacks electrophile, HOMO attacks LUMO. We're going to take the lone pair electrons on oxygen and overlap them with that sigma star. That's going to create a new bond. But because we're putting electrons into a sigma star antibonding orbital, what has to happen to the carbon-chlorine bond? Nice sound. No, that's a little too tennis. Yeah, that's good. Okay. Nope, didn't work. I'm gonna try that better. Nope, still not. Thank you. Got to work on that. Yeah, so it sounds like a week. My son Dallin has gotten to make. He's learned how to make that annoying drop of water sound that middle schoolers like to do in the middle of class to tick teachers off. Yeah. I'm waiting for somebody. There it is. There it is. Thank you. I never learned how to do that, so I'm actually jealous. Okay, so we make a new bond between the HOMO of the oxygen and where the LUMO is on the carbon, a new carbon-oxygen bond, and then we break the carbon-chlorine bond and the electrons actually leave with chlorine. This is called a substitution reaction. You don't need to worry about it now, but at some point in the near future, the words SN2 are going to become the bane of your existence. But when they do, understand that you already know why the reaction happens. The HOMO of the nucleophile attacks the LUMO of the electrophile. You make a new sigma bond and you break the old sigma bond. Yeah? Great question. Why does the HOMO attack the LUMO on carbon versus on chlorine? So the best way I found to answer this question is to just ask, okay, what would the products be if I instead made a new oxygen-chlorine bond and broke the chlorine-carbon bond? I would have a negatively charged carbon and a bond between oxygen and chlorine. This is actually hypochlorous acid. It's sort of bleach. So the oxygen-chlorine bond isn't that stable. And actually, I know that having a lone pair electrons on a negatively charged carbon is generally really unstable. You don't know that yet, but we're going to learn about tools to make that clearer. So it's just that the other way doesn't lead to stable products. Okay. Other questions? Yeah?
So just to clarify, the reason that the bond broke on the carbon chloride is because it wasn't anti-bonding?
That's right.
So that's how you knew it was going to it wasn't going to combine, but something was going to break.
Right. So the reason that the carbon-chlorine bond breaks is because we put electrons in the anti-bonding orbital.
And those electrons have to go somewhere, so they go.
Yeah, the electrons have to go somewhere. They go with the chlorine. We're actually going to call the chlorine the leaving group because it leaves with the electrons. Okay. There's a ton more, but this one maybe I will give you to ponder over the weekend. That's the first six-membered ring I've drawn in this class. Six-membered rings are not as hard as you think they are, not as difficult as you think they are, but rings of any kind I've discovered strike fear into the heart of OChem students. It's like the presence of the ring makes your brain stop remembering everything you already know. And so we're going to just have exposure aversion therapy or whatever it's called with respect to six-membered rings, so you get used to them. I'm going to tell you that this molecule is a nucleophile. I'm going to tell you that this molecule is, for the 30 seconds, the HCl is the electrophile. So you're going to want to identify what the HOMO is here, what the LUMO is there, and then I want you to predict what happens and draw the products. When you do that, you're going to generate, I'll give you a hint, you're going to generate two products which themselves could react with each other to generate a new product. Okay, so I want you to predict what the intermediate is, and then I want you to predict what the final product is, and you can do that by following through HOMO and LUMO. Okay, give that a try. If you need help, there should be information in the study guide. But I will just tell you guys, this is a chapter 10 reaction. which you will already be ready to deal with.